Welcome to the session on differentiation, stationary points. The objectives for this session are to find stationary points of functions and determine their nature. A stationary point on a curve is a point where the curve has gradient 0. A stationary point can be a local maximum, a local minimum, or a point of inflection. Note that we are showing parts of the curves here only. The nature of the stationary point can be determined by examining the gradient of the curve on both sides. So for curve y equals f of x, when f dash of x equals 0, we have a stationary point. If we look just before the x, or just before the turning point, on the maximum turning point, we can see that the gradient of f dash of x minus h is greater than 0. So just before the maximum, the gradient is greater than 0. At f of x, the gradient is 0. And after x, the gradient is less than 0. So f dash of x plus h is less than 0. Similarly, we can examine the minimum stationary point. Here, at x minus h, f dash of x minus h is less than 0. At x, f dash of x is equal to 0. And after x, at x plus h, f dash of x plus h is greater than 0. Again, for the point of inflection, let's have a look what happens just before the stationary point. So at x minus h, f dash of x minus h is greater than 0. At x, f dash of x is equal to 0. And after x, f dash of x plus h is greater than 0. And here's a summary. For a local maximum, f dash of x minus h is positive, f dash is 0, and f dash of x plus h is negative. For a local minimum, f dash of x minus h is negative, f dash of x is 0, and f dash of x plus h is positive. And for the point of inflection that you can see, f dash of x minus h is positive, f dash of x is 0, and f dash of x plus h is also positive. However, there is another type of point of inflection, and that is this one that you can see here. And this point of inflection has f dash of x minus h negative, f dash of x equal to 0, and f dash of x plus h also negative. Why do we call these points local maximum and local minimum? In the above, we have only shown parts of the functions. What happens beyond the endpoints? So at these points indicated here, if the pattern remains the same, then the points are maximum and minimum. However, if it changes, then the points are local maximum and local minimum. Here are examples of local maximum and minimum. Point A is a local maximum, as the function can take larger values, At A, this is the largest value in its immediate vicinity. And similarly, for point B is a local minimum, as the function can take smaller values. At B, this is the smallest value in its immediate vicinity. Let's now take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. Before we look at this example, let's examine the steps for finding the stationary points. First, find dy dx and put it equal to 0. Next, solve for x, and then substitute x in the original equation to find y. Now let's explore the steps to determine the type of stationary point that we have. We need to first find the gradients of values slightly greater and slightly less than this x, and then deduce the shape of the curve. So let's solve example 1a first. We are required to find the coordinates of the stationary points on the curve with the equation y equals x cubed plus 2x squared. So let's first find dy dx and put it equal to 0. Now y equals x cubed plus 2x squared. Recall the rules for differentiation. Hence, dy dx is equal to 3x squared, applying dy dx equals an times x to the power n minus 1, plus 4x, again applying the same formula. Let dy dx equal 0, and then we have 3x squared plus 4x equals 0. So let's now solve for x. Factorising gives us that x times 3x plus 4 equals 0. And therefore the stationary points are at x equals 0 and x equals minus 4 over 3. From here and from here. Now we substitute x in the original equation to find y. When x equals 0, we have that y equals 0 also. And when x equals minus 4 over 3, we simply substitute this value into the equation for y, and simplify to obtain y equals 1 and 5 over 27. So the stationary points are at 0, 0 and minus 1 and a third, comma, 1 and 5/27. Now let's have a go at example 1b. By considering points on both sides of each stationary point, determine whether it is a local maximum, a local minimum, or a point of inflection. For point 0, 0, consider the gradient on either side of x equals 0. The points which we are going to consider on either side of x equals 0 are x equals minus 0.1 and x equals 0.1. We know that at x equals 0, we have a gradient of 0, and therefore this is a stationary point. So the shape of the curve is simply flat, as shown. For x equals minus 0.1, we're going to substitute this value in the equation for dy dx. as shown, to give us a negative value. So at x equals minus 0.1, we have a negative gradient, and therefore the shape of the curve is as shown in the table. Let's do likewise for x equals 0.1. Plug this value in to dy dx. This time we obtain a positive value. Therefore, at x equals 0.1, the gradient is positive and the shape of the curve is as shown. And therefore, we have that 0, 0 is a local minimum. Now let's look at the other stationary point. We're going to find the gradient on both sides of x equals minus 1.3. We are in particular going to look at the points x equals minus 1.4 and x equals minus 1.2. Of course, we know that the gradient at x equals minus 1.33 recurring is equal to 0. So the shape of the curve is actually flat at that point. At x equals minus 1.4, again, we simply plug into the equation for dy dx as shown, and this gives us a positive value. So our curve is sloping as shown in the table. And now let's plug in the value for x equals minus 1.2 into our equation for dy dx, as shown. And this gives us a negative value. So our curve is sloping the other way. And therefore, this stationary point is a local maximum. Sometimes you can use the second order derivative f double dash of x or d2y dx squared to find the nature of the stationary point also. How do we do this? The second derivative f double dash of x gives the rate of change of the gradient function. At a stationary point x equals a, when f double dash of x is greater than 0, then the gradient is increasing from a negative to a positive value. So the stationary point is minimum. So at a stationary point x equals a, if f double dash of a is greater than 0, we have a local minimum. Now when f double dash of x is less than 0, the gradient is decreasing from a positive to a negative value. So the stationary point is a maximum. And therefore, if f double dash of a is less than 0, then we have a local maximum. Now, if f double dash of a equals 0, then we actually can't say anything, and we need to use the other method. Let's now take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve example 2a first. Find the coordinates of the stationary points on the curve with equation y equals 2x cubed minus 15x squared plus 36x plus 2. Remind yourself of the rules for differentiation shown at the bottom of your screen. And let's solve. So applying the rule for differentiation, gives us dy dx equals 6x squared minus 30x plus 36. And factorising gives us dy dx equals 6 times x minus 2 times x minus 3. If we put dy dx equal to 0, we have that either x equals 2 or x equals 3. Now let's substitute x equals 2 in the equation for y to obtain the y value. So plugging in x equals 2 in the equation for y, gives us y equals 30. Now when x equals 3, we plug in the value x equals 3 into the equation for y, as shown, to give us y equals 29. So when x equals 2, y equals 30, and when x equals 3, y equals 29. So the stationary points are 2, 30 and 3, 29. Now let's solve part B. We are required to find d2y dx squared and use it to determine the nature of the stationary points. Recall the steps to determine the type of stationary point. Remember, if d2y dx squared is greater than 0, we have a local minimum. If it's less than 0, we have a local maximum. And if it's equal to 0, we can't say, and we need to use another method. So let's solve this. So let's summarize the information that we already have. We have the equation for y. We also have from part A the stationary points, and we can remind ourselves of the rules for differentiation at the bottom of the screen. So we can now find d2y dx squared. Applying the formula a second time, we obtain d2y dx squared equals 12x minus 30. Remember that differentiating 6x squared gives us 12x, and differentiating minus 30x plus 36 gives us minus 30. When x equals 2, which is one of the stationary points, d2y dx squared equals minus 6. This is less than 0, and therefore 2, 30 is a local maximum. Now when x equals 3, d2y dx squared equals 6. Clearly this is positive. And therefore 329 is a local minimum. Now let's have a go at another example. Pause the video and have a go. Press play when you're ready to view the solutions. Let's remind ourselves of the rules for differentiation first. And now let's have a look at example 3a. The curve with equation y equals 6 over x plus 8x cubed has stationary points at x equals plus or minus a. Find the value of a. So let's solve this. We know that y equals 6x to the minus 1 plus 8x cubed. We've put it in this form so that we can differentiate easily. So differentiating gives us dy dx equals minus 6x to the minus 2 plus 24x squared. Now let's put dy dx equal to 0 to find the stationary points. So of course this implies minus 6x to the minus 2 plus 24x squared equals 0. And so multiplying out by x squared gives us minus 6 plus 24x to the 4 equals 0. And solving for x gives us x to the 4 equals 1 over 4. And therefore x equals plus or minus 1 over root 2. Hence we have that a equals 1 over root 2. Now let's sketch the graph of y equals 6 over x plus 8x cubed. So here is the key information from part A. When x equals 1 over root 2, substituting this into the equation for y gives us that y equals 6 root 2 plus 8 over root 2 cubed. And tidying up gives us that y equals 8 root 2 at this point. Now let's find d2y dx squared in order to find the nature of this turning point. d2y dx squared is equal to 12x to the minus 3 plus 48x. And so plugging in x equals 1 over root 2 into the equation for d2y dx squared gives us that d2y dx squared is greater than 0 at this point. And therefore we have a local minimum. Now let's look at the other stationary point, x equals minus 1 over root 2, and plug that in to the equation for y. Tidying up gives us y equals minus 8 root 2. And so we have a stationary point at x equals minus 1 over root 2, y equals minus 8 root 2. Now let's differentiate again in order to find the nature of this turning point. So differentiating again gives us d2y dx squared equals 12x to the minus 3 plus 48x. And so when x equals minus 1 over root 2, d2y dx squared is less than 0. And of course this implies that our stationary point is a local maximum. Here's the key information that we have from part B. We can use that to plot our graph. Remember that one of our stationary points was 1 over root 2, h root 2, and that was a local minimum, which is here. The other stationary point was here. It was a local maximum. We also have an asymptote at x equals 0, because y equals 6 over x, so clearly we're never going to actually get a value for x equals 0. We also can look at what happens when x tends to 0 from the positive side. When that's happening, clearly we're getting larger and larger and larger values of y, and therefore y tends to infinity as x approaches 0 from above. And when x approaches 0 from below, y tends to minus infinity. So here's our graph. This brings us to the end of this session. If you have understood its contents, you should be able to find stationary points of functions and determine their nature. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.